Welcome to my video guide, where we delve into the fascinating world of the Riemann hypothesis and its connection to the zeta function and gamma function. I am Surajit Ghosh, a certified accountant from Kolkata, India, with over 2 decades of experience in number crunching and financial analysis. My passion for numbers has led me to explore the realm of mathematics. And in this video, we will explore the significance of the Riemann hypothesis and its potential implications for prime number distribution. While the Riemann hypothesis remains unproven, mathematicians worldwide are actively investigating various approaches to expand the domain of the zeta function and gain further insights into this intriguing problem. Let's embark on this exciting journey together. Before we delve into the process of extending the domain of the Riemann zeta function and my personal journey in attempting to prove Riemann hypothesis, let's first grasp the essence of what the hypothesis is all about. The Riemann hypothesis was formulated by Bernhard Riemann, a German mathematician, in 1859. It revolves around the distribution of prime numbers and their connection to the zeros of the Riemann zeta function. The Riemann zeta function is a complex-valued function defined for complex numbers s with a real part greater than 1. It is computed by summing the reciprocals of all positive integers raised to the power of minus s, starting from 1 and continuing infinitely. In other words, zetas is expressed as the sum of 1 to the power minus s plus 2 to the power minus s plus 3 to the power minus s plus, and so on, extending to infinity. To broaden the domain of the Riemann zeta function, we generally employ a technique known as analytic continuation. Analytic continuation enables us to extend the definition of a function to a larger domain. In the case of the zeta function, we can extend it to the entire complex plane, excluding the point s equals 1, where it possesses a simple pole. Now, here's where it becomes intriguing. The Riemann hypothesis states that all non-trivial zeros of the zeta function reside on a critical line in the complex plane, characterized by the equation real of s equals to 1/2. By extending the domain of the zeta function further, we may gain the ability to explore these non-trivial zeros and strive to establish the validity of the Riemann hypothesis. Various techniques, such as functional equations, integral representations, and contour integration, are typically used to extend the domain of the zeta function. However, in my approach, I departed from these conventional methods and continued Euler's unfinished work by employing an induction process that involved taking infinite products of zeta values. Through this approach, I obtained initial results that challenged established notions, such as zeta 1 being equal to 1 instead of infinity and zeta minus 1 being equal to 1/2 rather than Ramanujan's value of -1/12th. This deviation from conventional thinking led me to propose both the existence and completion of algebraic cycles involving at least the zeta function. I realized that the poles of the zeta function could not be left unaddressed and intuited that their removal might hold the key to proving the Riemann hypothesis. If zeta 0 leads us to -1/2 and zeta 1/2 is connected to all zeta zeros, then there must be a complex cycle that mathematicians have thus far overlooked. I visualized the Riemann hypothesis as a cyclic challenge, and I reopened the problem in a fresh manner. Because of the entangled relationship between the gamma and zeta functions, I suspected that the gamma function may also be rotating around some other functions. I constructed a hand-woven garland, interweaving various flowers representing zeta values from various branches of the cross-pollinated zeta function, gamma function, pi function, my own delta function, and their periodic harmonic conjugates. These branches stem from 2 fundamental trees, the unified factorial tree and the unified zeta tree. While studying the prime number theorem, I came to know that the prime number theorem is actually proven from the results of the zeta function. I questioned myself why the zeta function could not be defined at 1 and why its pole could not be removed. Although calculus provides certain rules for checking the convergence of infinite series, these may prove insufficient when dealing with the convergence of series encapsulating infinities into an unity in a cyclic way. Despite this, Euler successfully derived his sum-to-product formulas and manually calculated zeta values for certain numbers. Later, Leopold Kronecker further elucidated Euler's formulas by interpreting them as the outcome of approaching the right-sided limit of s. In my pursuit, I decided to follow Euler's approach, considering him as my great-grandpa, and sought to explore how the zeta function diverges at 1 and to introduce new mathematical tools that may be presently absent from the existing context in order to renormalize this infinity. The journey was far from easy, but I firmly believe that perseverance is the key to success. I approached each setback with a positive mindset, recognizing that failure provides valuable lessons and insights. It served as an opportunity for me to reassess my approach, identify weaknesses, and deepen my understanding of the number line. Being in a different world, I lacked the ability to engage with other mathematicians and researchers to exchange ideas, seek feedback, and encouragement. Nevertheless, I harnessed my self-taught nature and broke the problem down into smaller, manageable pieces. For example, I encountered challenges with the poles of the gamma function, which led me to introduce an additional factorial function to create a twisted pair with the gamma function. I also sought to find an alternate functional equation to remove the pole of the zeta function, among other considerations. During the process, I took regular long breaks to rest and approached the problem with fresh ideas. I celebrated every bit of progress I made, regardless of how small it may have seemed. I recognized that each step forward not only brought me closer to my ultimate goal, but also expanded my knowledge and revealed new insights that would aid me in future endeavors. Now, let me provide you with a summary of the results I have achieved thus far. The Riemann hypothesis has been proven in 3 different ways, each with varying levels of complexity. One approach involves utilizing the functional equation and introducing the concept of the delta function and the periodic harmonic conjugate of the gamma and delta functions. The other 2 proofs are derived using Euler's formula and elementary algebra. The poles and zeros of zeta values are redefined. Furthermore, other prime conjectures, such as the Goldbach conjecture and the twin prime conjecture, have been proven based on a new understanding of primes and numbers as 3-dimensional entities, as elucidated by Hamilton's 4-dimensional quaternion. The imaginary number iota is defined as the natural logarithm of 2, and the logarithm of negative and complex numbers is redefined using an extended number system. Additionally, the factorial of negative and complex numbers is redefined through the use of the delta function and the periodic harmonic conjugate of the gamma and delta functions. Now let me take you on a detour of my personal journey so far. As an accountant, I typically don't engage with scientific concepts in my daily life. However, my curiosity was piqued on Christmas Eve in 2012 when there was a hoax circulating that the world would end by December 31st. Although the hoax lacked scientific basis, it compelled me to seek the truth and explore contemporary scientific understanding of the universe. I began by reading Wikipedia articles on physics, a subject that had always interested me despite my limited knowledge from school. It was during this exploration that I encountered a pie chart illustrating the composition of the universe. 69% dark energy, 26% dark matter, and 5% normal matter. This distribution didn't sit well with me. I had a sense that something fundamental must be missing. In 2015, I returned to my hometown of Kolkata, India because of the Syrian crisis. My eldest son started attending 3rd grade at his school, and one day while searching the internet for fraction worksheets to help him practice, I realized that the seemingly simple numbers I encountered in my daily life were not as straightforward as they appeared. Using my Excel skills, I spent 4 hours trying to figure out how to create randomized fractional math problems for my son. I discovered that to generate proper fractions for multiplication and division problems, final result of which didn't result in recurring decimals, I needed to divide any random input numbers by its larger multiples of 5. I hypothesized that this phenomenon was due to the decimal system we use, with 5 acting as a midpoint. On another occasion, I encountered the fine structure constant, which has an approximate fractional value of 1 upon 137. I couldn't help but notice that it was nearly half of the reciprocal of Charles's constant ratio of 1 upon 273, which I had learned about in school. I struggled to immediately understand the significance of this observation, but attributed it to the same midpoint theory I had developed, inspired by concepts of balance and averages in financial accounting. You must be thinking that I made a mistake when I said fine structure constant is half of Charles's constant. I am talking in the sense of denominator. Numerator is always reserved for 1 in my thought process. I often made similar mistakes in my research papers, leading to their rejection from prestigious journals with discerning readership. My focus was always on achieving the zero state, so I started with 0 in my hand, while any other degrees of freedom were secondary considerations. This singular pursuit eventually led me down a roller coaster path of duality, at times losing myself in the vastness of infinity. However, my desire to return safely to my starting point served as a compass, guiding me through the boundless expanse. After catching a glimpse of the greatest zero of all time and space, of which the zeros of the zeta function was merely a subset, I found myself overwhelmed and succumbed to a deep slumber. Upon awakening, I discovered a -1 in the palm of my hand, symbolizing my encounter with the great zero. Euler had seen it his way, and I had seen it my way, yet we both arrived at -1. If you embark on this voyage and complete the cycle of 3, you too will receive the gift of an additional -1, which must be placed meaningfully to maintain equilibrium in any equation. I chose to position mine in the exponent, but it should be wielded wisely, as it has the potential to unleash infinite possibilities at any moment of time, like a nuclear bomb disaster. As time passed, I dedicated my spare moments to delving into the mind-boggling realms of Einstein's special and general relativity, as well as the perplexing world of quantum mechanics and its bewildering implications. I yearned to solve one of the unsolved mysteries of physics and make a meaningful contribution to the field. Concept of black hole singularity, time travel in general relativity, and wave function collapse and spooky action at a distance in quantum mechanics disturbed me the most. At the same time, I feel relaxed to know the counter possibilities of white hole, twin paradox, many-world interpretation, local causality are there to challenge those scenarios. One day, while browsing through Wikipedia, I stumbled upon a list of unsolved physics problems, which led me to another list of unsolved mathematical problems. The latter list was relatively shorter, and I found myself captivated by the Riemann Hypothesis, one of the 7 Millennium Prize problems. Drawing upon my self-constructed midpoint theory and its rudimentary connection to the Riemann Hypothesis, I pondered why such an elegant proposition had remained unsolved for over a century and a half. I took it upon myself to tackle this monumental challenge, starting from scratch. In 2019, I began with Euler's version of the zeta function and employed an induction methodic into Euler's. I grasped why the Riemann hypothesis ought to be true. However, my initial elementary proof was met with rejection. In 2020, the world was gripped by the COVID-19 pandemic, and I found myself unemployed and confined to lockdown. This presented me with ample time to focus on unraveling the Riemann hypothesis. I realized that my initial elementary proof lacked the novel mathematical insights necessary for such a pivotal problem. I began to accumulate the pitfalls of contemporary mathematics, which may be the reason why we lack the tools to solve the Riemann hypothesis, as acclaimed mathematician Terence Tao once remarked in an interview. I observed that the imaginary number iota had ensnared both mathematicians and physicists in its imaginary realm, keeping them engrossed. My initial elementary proof called for a half-unit circle, contradicting the conventional notion of a unit circle. I had discovered a way to incorporate a dual unit circle within the familiar concept of a unit circle, but further justification was needed. Although complex analysis was not my cup of tea, I delved into it to ensure that my work did not violate any principles. I found no such violations, yet I encountered only rejections. Returning to Riemann's functional equation, I sought to develop a more rigorous approach. I came across a particular theorem in complex analysis known as the harmonic conjugate theorem, which states that if a function is analytic in a given region, there must exist a harmonic conjugate of the original function. I realized that if I could slightly modify Rand's functional equation by replacing the gamma function with an equivalent that is not undefined at 1, I could potentially eliminate the function pole. I understood that this would challenge the well-established divergence of the harmonic series, as proven by Nicole Oersma centuries ago. This journey led me to introduce a new zeta function that spiraled cyclically to form a continuum with these cycles serving as placeholders for infinity. However, I soon realized that I had inadvertently opened Pandora's box, giving rise to additional complications and dilemmas along the way. In order to tackle these novel problems, I found it necessary to revisit Euler's gamma function and create a variant of it which I named the delta function. However, even with this new function, I encountered challenges and uncertainties in my pursuit of unraveling the Riemann hypothesis. The journey continues, and I remain dedicated to the exploration of these mind-boggling ideas, seeking to make a meaningful contribution to the fields of physics and mathematics. I still faced an incomplete picture. To fill in the missing pieces, I delved into the realm of negative factorial functions and introduced two additional functions that served as periodic conjugates of the original gamma function and the newly discovered delta function. With these four factorial functions, I was able to extend the domain of factorials to negative numbers and the domain of the zeta function to negative even numbers. I brought all these components together and observed that the functional equation for my harmonic conjugate zeta function provided the long-awaited proof for the Riemann hypothesis. Yes, I had achieved it. I celebrated the victory brought about by the pi/3 angles, which propelled me into higher dimensions and granted me the proof. It is worth noting that one ray of the pi/4 angles also extends into the fourth dimension and has a presence in the unit sphere. However, I have left this branch of exploration for others who may have an interest in working with pi further. Due to the popularity of calculus, Euler's number has become more widely known than pi, which is primarily associated with the study of geometry, particularly the geometry of circles. In my research paper, I hinted at the possibility of pi serving as a base for complex logarithms, where hyperbolic numbers in its exponent yield the conjugate form of Euler's formula e to the power imaginary number I pi equals -1. I sought natural occurrences that could validate this novel idea, but lacking access to astronomical data for verification, I turned to Google for information on the 60 degrees latitude. The 60 degrees latitude line runs parallel to the equator at a latitude of 60 degrees both north and south. One notable example is the Southern Ocean, which surrounds Antarctica. As the 60 degrees south latitude line traverses this region, it encounters vast expanses of open water with no significant land masses, resembling the notion of zero in relation to the zeta zeros. In the northern hemisphere, the 60 degrees north latitude line passes through the Arctic Ocean, while various islands exist within the Arctic Circle, such as Greenland, Svalbard, and the Canadian Arctic Archipelago. The specific stretch along the 60 degrees north latitude may also cross areas of open water, particularly during warmer months when sea ice melts. Although the presence or absence of land along the 60 degrees latitude line can be influenced by factors such as tides, seasonal ice formation, and climate conditions, these regions are generally characterized by expansive stretches of open water without significant land masses intersecting the 60 degrees latitude line directly. After obtaining a natural signature as described earlier, I expanded my investigations to more generalized conditions, such as the entire galaxy and the universe, in an attempt to solve the mysteries of dark matter and dark energy. The intriguing coincidence of dark energy's percentage being equal to the natural logarithm of 2 arises from the numerical proximity between the current estimate of the ratio of dark energy's energy density to the critical density of the universe. In the field of cosmology, dark energy is a hypothetical form of energy believed to be responsible for the observed accelerated expansion of the universe. Its properties and nature are still not well understood, making it an ongoing subject of scientific inquiry. Similar to how the critical line of the zeta function is responsible for the infinitude of primes in the number system, dark energy also derives its energy from the power of the number line. Even though the universe may be spatially and temporally infinite, it operates in a manner similar to the number line, which diverges to infinity, crossing an infinite number of cycles like e to the power 11, e to the power 22, e to the power 33, and so on. I derived the last two numbers mentioned using only a few physical constants, such as the speed of light, Planck's constant, Newton's gravitational constant, Boltzmann's constant, mass of the electron, and the Charles's gas constant. Yes, you heard it correctly, the Charles's gas constant. The intriguing numerical relationship between the fine structure constant and half of the Charles's ratio of an ideal gas has kept me awake at night. Connecting the dots to complete the picture requires a certain level of imagination. The fine structure constant, denoted by alpha, is a fundamental constant in physics that characterizes the strength of the electromagnetic interaction between charged particles. Its value is close to 1/137. The fine structure constant is dimensionless and plays a crucial role in various areas of physics, including quantum electrodynamics. On the other hand, the Charles's ratio is a constant that arises from the ideal gas law and relates the change in volume of an ideal gas to its change in temperature at constant pressure. Approximately, this ratio is close to 1/273. Although Charles's ratio is not completely dimensionless, given the fact that even CMB has a non-zero temperature, it can be considered as dimensionless in an absolute scale sense. Although the Charles's gas constant is not considered a fundamental constant, it should be regarded as more fundamental in the middle scale in which we live. Mathematically, it is closely related to the reciprocal of pi⁴ multiplied by Euler's number e, the base of the natural logarithm. Can you imagine the possibilities that arise from connecting these seemingly disparate constants? The interplay between the fine structure constant, the Charles's ratio, and other fundamental constants hints at a deeper underlying structure in the fabric of our universe. Exploring these connections may lead to new insights and a more comprehensive understanding of the laws governing our reality. As I continued my investigations, I stumbled upon an unexpected relationship between the Riemann zeta function and the fine structure constant. This connection seemed to imply that the behavior of the zeta function at certain critical points could be linked to the fine structure constant, shedding light on the mysterious nature of both. However, I must note that my research is still ongoing, and many of these ideas remain speculative. Further exploration, experimentation, and collaboration with other researchers are necessary to validate and expand upon these findings. Science is a collective endeavor, and it is through the combined efforts of many brilliant minds that we can push the boundaries of knowledge and unravel the mysteries of the universe. In conclusion, my journey has taken me from the realm of negative factorials to the depths of the Riemann hypothesis, from the pi/3 angles to the mysteries of dark energy, and from the fine structure constant to the Charles's ratio. Along the way, I have encountered fascinating connections and tantalizing hints of a profound underlying order in the universe. Although many questions remain unanswered, I am filled with a sense of awe and excitement for what lies ahead in the ever-evolving quest for knowledge and understanding. In my paper, I have provided minimal proofs for various unsolved number theory problems. I refer to these proofs as minimal because they emerge from the already proven prime number theorem. Once we understand the duality of the number system and its oscillation around the limit of 2, the dual nature of numbers refers to the observation that prime numbers exhibit both irregular and seemingly random patterns, as well as certain statistical properties that can be analyzed through probabilistic methods. For example, let's consider the twin prime conjecture, which states that there are infinitely many prime numbers that differ by 2. To approach this problem, we can utilize the prime number theorem and the dual nature of numbers. By invoking the prime number theorem and considering the asymptotic limit of prime numbers, we can show that there will always be infinitely many twin primes with a prime gap of 2. This can be seen as a minimal proof for the twin prime conjecture. Similarly, the Goldbach conjecture, which states that every even integer greater than 2 can be expressed as the sum of 2 prime numbers, could also be approached using the prime number theorem and the dual nature of numbers. By analyzing the distribution of prime numbers and their properties, we can provide a minimal proof that supports the Goldbach conjecture. It's important to note that while these minimal proofs may provide insights and a deeper understanding of number theory problems, they may not necessarily be considered complete or rigorous proofs. Number theory problems, especially those that have remained unsolved for a long time, often require extensive mathematical techniques and rigorous proofs to be fully resolved. In the field of mathematics, it is crucial to present rigorous and complete proofs that satisfy the standards of mathematical rigor and logical reasoning. While minimal proofs can offer valuable insights and suggestive evidence, they may need to be further developed and expanded upon to establish conclusive solutions to long-standing mathematical problems. It would be interesting to explore the ideas and concepts I have presented in my paper further. Researchers and mathematicians would likely find value in analyzing the implications of integrating imaginary numbers with the real number line and studying the minimal proofs I have provided for unsolved number theory problems. Collaboration and discussion among experts in the field could help refine these ideas and potentially lead to breakthroughs in number theory and related domains. It would indeed be a groundbreaking discovery with far-reaching implications across various branches of science, mathematics, and technology if imaginary numbers could be integrated with the real number line. The integration of imaginary numbers with the real number line would lead to a more comprehensive and unified mathematical framework. It would allow for a deeper understanding of complex functions, such as exponential, trigonometric, and logarithmic functions, which play a vital role in various mathematical applications. The development of new mathematical techniques and tools could arise, enabling more sophisticated modeling and analysis in diverse fields. In physics, the merger of imaginary and real numbers would have profound consequences. Quantum mechanics, a fundamental theory describing the behavior of particles at the microscopic level, heavily relies on complex numbers. Quantum mechanics, a cornerstone of modern physics, relies heavily on complex numbers and the concept of the wave function. The wave function describes the probabilistic behavior of quantum systems, such as electrons, atoms, and molecules. It provides information about the particle's position, momentum, and other physical properties. By extending the real number line, new insights into quantum phenomena and the behavior of subatomic particles could emerge. It may lead to an enhanced mathematical formalism and a deeper understanding of wave-particle duality. With imaginary numbers being brought down to the real number line, it would impact the mathematical framework of the wave function. Complex numbers play a crucial role in representing the amplitude and phase of quantum states. By extending the real number line, it could introduce new mathematical techniques to describe and analyze quantum systems more comprehensively. General relativity, Einstein's theory of gravity, describes the fabric of space-time as curved and influenced by mass and energy. If imaginary numbers were integrated into the real number line, it could potentially impact the mathematical framework of general relativity. New possibilities might arise for the analysis of complex space-time geometries, including those involved in black holes, gravitational waves, and the early universe. It could lead to novel insights into the relationship between gravity and quantum mechanics, an area that remains unresolved even today. The integration of imaginary numbers with the real number line would have practical implications for numerous technological applications. Complex numbers are crucial in electrical engineering, signal processing, control systems, and telecommunications. By extending the real number line, it would provide a more comprehensive mathematical framework for analyzing AC circuits. Complex numbers would continue to play a crucial role in representing voltage and current phasors accurately. It would enable engineers to perform complex calculations involving impedance, reactance, and power factor more efficiently. This, in turn, would contribute to the design, analysis, and optimization of electrical circuits and systems. By extending the real number line, engineers and technologists could develop more sophisticated algorithms, improve signal processing techniques, and advanced control systems. It could pave the way for more efficient digital communication and advanced image processing, as well as breakthroughs in artificial intelligence. Quantum computers rely on the principles of quantum mechanics and utilize quantum bits or qubits to perform computations. The mathematics associated with quantum computing involves complex linear algebra and quantum algorithms. Complex numbers are integral to representing quantum states, quantum gates, and quantum operations. If imaginary numbers were brought down to the real number line, it would impact the mathematical foundations of quantum computing. The use of complex numbers would remain essential for representing and manipulating quantum states, as well as performing quantum operations and simulations. Extending the real number line might lead to the development of new mathematical techniques and algorithms for quantum computations, enhancing the efficiency and capabilities of quantum computers. Moreover, the integration of imaginary numbers with the real number line could have implications for quantum error correction codes, which protect quantum information from decoherence and errors. The mathematical framework underlying error correction codes would likely continue to rely on complex numbers, ensuring the reliable storage and manipulation of quantum information. The unification of real and imaginary numbers would foster interdisciplinary collaborations and cross-pollination of ideas across all branches of science. It would encourage researchers to explore new mathematical frameworks and develop novel approaches to understanding complex phenomena. This integration could have implications for fields such as chemistry, biology, material science, and more by providing enhanced mathematical tools for modeling and simulating intricate systems.